Bill, thank you so much for joining. We'll give others a few moments here, maybe a couple minutes before we start.
Yeah, we've got a number of people in the waiting room.
Okay.
Coming in. So yeah, maybe we can wait maybe another 3 or 4 minutes. Jerry's coming in too.
I recognize Mitch Shewan. We go back a few years from the hydrogen days, right?
You got it.
Hydrogen fuel cells.
It's still the hydrogen days for Mitch.
Yep. Yeah, he's rode the troughs and valleys, or the peaks and valleys.
That's it, man.
How you doing, Bill?
Doing great.
Is Vicky here?
Yes, she
Vicky,
is.
sure. Oh, there she is. Yeah. Hey, Vicky. Are you traveling? Are you?
No, I'm back in Kona now. I was traveling. I was in Honolulu. Now I got home last night.
Got it.
Well, nice to see you, Vicky. We've talked several times on the phone, but never with video on.
Yeah, it's good to see you, Bill. And thank you for agreeing to do this talk and help everybody. I think they'll be really excited to hear about this new technology that will assist with getting the power density we need without relying on the lithium, and be more sustainably chemistry and cost effective.
All those good things, right?
So, okay, we've got Dr. Luis Vega is joining us. What I'm going to do is I'm going to, Bill, I trust you have a PowerPoint you're going to want to do a screen share. So what I'm going to do is I am going to make you co-host. And hang on just a second. Make co-host. Okay, I'm going to make you co-host so that you'll be able to share as you wish.
Okay. Yeah, I kind of have maybe a 15-20 minute set of slides.
Okay.
We can extend it longer. Feel free to interrupt me, or we can have a Q&A type session at the end.
Okay.
Bill, and time check. What is your expectation on time?
Well, we want to hear what you have to say. So I think what you just described will fit within your ability to present and our ability to ask questions. There's a lot of people with some skills here who will probably have a lot because the technology
you mean
you're bringing.
Opinions?
Yeah, thoughts.
Bill, is this the same
observations
that you just made to AEE?
Is that Ray?
That's Russ. Is it the same?
Russ. Yes, I was going to use the same deck. Yes.
Okay.
Sorry, I don't have any new exciting slides for you.
That's all right.
Although maybe I'll go look and see if I have something I can pull out that'll surprise you.
Oh, so Peter, Dave, when you're ready for me to kick it off, just let me know and I'll get us started.
Yeah, I think it looks like we've got a pretty good group here. I'll just keep an eye out and let people in as they go. So why don't you go ahead and kick off? We can introduce ourselves to Bill and do that thing.
Yeah. So first of all, thanks very much for everyone for joining us for this SEH Sustainable Energy Hawaii Pau Hana. I see a lot of familiar faces. We also have some new people here. So we'll take a moment in a little bit to go around the room and just quickly introduce ourselves, where we're coming from, and then we'll hop into the event for today. I will say that we are recording this event, this session, with the intent of socializing it with our mailing list. It's going to get on our social media as well as our website. So just take note of that. And so before I introduce you, Bill, maybe we'll just do a quick round. I'm one of the board members for SEH. Peter?
Peter Sternlight, board member, SEH.
Pass it along.
And Stan?
Stan Osterman, former commander of the Hawaii Air National Guard and board member of Sustainable Energy Hawaii, also formerly director of Hawaii Center for Advanced Transportation Technologies and Hydrogen Junkie. Vicky?
I'm Vicki Newman. I'm with the 9th Mission Support Command, Army Reserve, and I'm a Resource Efficiency Manager in Honolulu, and I support the Pacific Rim. I met Bill and his technology, and I thought it was a good idea to bring it to the group to share. Dave R.
Ron.
Yeah, I'm Ron Riley, Volcano Village, Hawaii, Citizens Climate Lobby, Hawaii.
Excellent. Dave Rand.
Hi guys, Dave Rand. Peter invited me. I was a visual effects artist for Peter back when he was president of Rainmaker. Worked on movies like Batman and Flubber, and thanks to him. Before that, I was his stockbroker, pitching Ballard Power and Fuel Cell International. Peter just thought I'd be interested in this, so I appreciate you guys letting me listen in.
Welcome. So let's see. I've lost Mitch. I couldn't to help me here. It's been Noel.
Go ahead, Mitch.
Muted.
You're muted.
You're muted.
That's probably a good thing. I'm Mitch Ewan with the Hawaii Natural Energy Institute, where I'm the Hydrogen Systems Program Manager, and I operate currently one of the only of 2 hydrogen stations in Hawaii, and this one over my background is on the Big Island of Hawaii at Nelha.
Thanks, Mitch. Keith.
Keith Neal, several decades in aerospace engineering and long-term interest in energy environment.
John Cross.
Okay, John Cross. I'm land manager for Ed Olson Trust. Some 13,000 acres of land in Hawaii. And interested in energy always.
Thanks, John. Virginia.
I'm a member of Citizens Climate Lobby Hawaii, and I'm on Oahu.
Thanks, Virginia. Gary.
I'm Gary Rosenberg in Curtistown. I raise animals and plants regeneratively, and am trying to develop a system to transition to a local economy as far as food systems and energy systems. And I'm just trying to create collective units here in Hawaii to demonstrate that model.
Thanks, Gary. Russ, did you already introduce yourself?
No.
Go ahead.
No, Russ Kohler, president of the Association of Energy Engineers Hawaii chapter, and new company, Go Green Alternative Energy Solutions.
Go Green. John Carroll.
Yeah, I'm John Carroll. I'm a plant researcher. I'm working on a Department of Energy grant for sustainable aviation fuel, and my focus is on plant-based energy systems.
Great. Thanks, John. Jerry?
Hi, Jerry Changs, former state representative and a SEH board member.
Thanks, Jerry. Hal? You're muted, Hal.
Yeah, okay. Retired urban planner with the UN for about 15 years and retired urban planner for City and County of Honolulu for 10 years.
Thanks, Hal. Dave?
Dave, oh, you're talking to me?
No, David Deleuze.
Oh, sorry.
Hi, David Deleuze. I have interest in energy solutions and SEH board member.
Thanks. Sid?
Aloha, Sid Higa. I'm with Ho'olu Holdings and also a member of the Renew Rebuild Hawaii consortium to spread energy and other news out there. Working with some farmers out here, and we're looking to plant hemp. So hemp might be an alternative fuel source, feedstock source for some of the fuels that might be brought up here.
Thanks, Sid. Caroline?
Caroline, concerned citizen.
Thanks, Caroline. Paul?
Yeah, hi, I'm Paul Pontio. I'm the director and CTO for Blue Planet Research. Also, H2 Energy Hawaii and EMC2 Technologies.
Thanks,
All
Paul.
here in Kona on the Big Island.
Thank you. Serene? We're almost done. Go ahead.
Hi. Hope you can hear me well. I'm Serene, Hawaii State Energy Office Clean Energy Wayfinder and a community listener. So I'll be listening to this iron battery presentation, and I'm grateful to be among all you accomplished.
Thank you. Thank you. Is it Sequoia?
It is. So yeah, Sequoia, thank you so much for having sent an invitation about this. I think I'm going to have to join this more often. I am on the board of Oahu Renewable Energy Cooperative Molokai and involved with the island-wide renewable energy planning for the whole place. So very excited about this.
Excellent.
Yeah.
Thanks for being here. And is it Kyle? Last but not least.
Yes. Thank you. Yes, Kyle Anderson, Burns and McDonnell, and Geothermal Rising.
Excellent. So, Bill, I thought it might be good for you to get a feel for who is interested in this really important space that you're going to enlighten us on today. And it's a very diverse group all over the state, and we're very, very keen on figuring out how to enable a just and effective transition. As we continue to explore all of these different solutions, as far as energy storage is concerned, we've come across this topic that you're about to talk about with regard to flow batteries. So we look forward to learning quite a bit about it tonight. And if you don't mind, I'll give you a few moments to introduce yourself, and then you can jump into the presentation. Thank you.
Absolutely. Thank you, Noah. I am very impressed with the diversity of the crowd, both in terms of experience and geography and all. Just to give you a little background on me, I started out in aerospace with Honeywell for about 15 years, then jumped over into kind of high-tech flat panel displays. And then in 2003, jumped over into the energy space with a startup in the fuel cell space. And that's where Mitch and I initially met. We were building a combined heat power 5 kilowatt high temperature PEM fuel cell at the time, and trying to make that commercially viable. It took me about 7 years to figure out that it was very difficult to make it cost effective and competitive. So that's when I jumped over to solar. And I was with Solyndra and Solar World, spent time in Hawaii developing some commercial scale projects. And then some of the people, or a couple of the people that were in the fuel cell business with me, had gone off to start working on a flow battery, and had picked up the dominant flow battery at the time, and I would say still most tried flow battery is a vanadium flow battery. That's what they started out working on. But funny story, they were operating out of the garage like all good startups should, and they couldn't get the chemicals for vanadium flow batteries delivered to a residential address. So that made them start thinking about there might be some other more friendly type chemicals and earth abundant type materials that might lend itself to a low cost flow battery technology. And that's in 2011, they jumped over to the iron flow technology. So I've spent, I haven't lived in Hawaii, but I've spent probably 5 or 6 years of my life commuting from Portland over there for either solar or batteries, or even a stint doing LED lighting back when that came on the scene a little while back. So I appreciate the opportunity. Why don't I jump into a little slide presentation? Feel free to speak up and interrupt me if you've got questions. I'll kind of try to pause to allow people to ask questions, but don't worry about interrupting me. Let's see if this works here. I'm used to using Teams, so Zoom, it looks like I got it here.
You got it.
All right, let's see if I can even take it to a full screen. Guess I got to do that on the PowerPoint.
Yeah, probably if you go into slideshow mode.
There we go. Does that work?
Yep.
Okay. I'll whip through this part. This is kind of the business side of it. As I mentioned, we started the company back in 2011. it wasn't until about 2015 that we put the first full system out in the field. And that's when the learning really started. As most of you with experience in these different energy spaces, until you get that technology into the field, you really don't know what you've got or how far you are away from commercialization. So 2015 till about 2020, then we settled in on a design, and we call it the energy warehouse. That's actually that single container that you see in those pictures there. And our focus from the beginning, as I kind of alluded to, is trying to develop the lowest cost, long duration energy storage technology that we could. The key element that segregates us or separates us from the lithium ion is the long duration. So we're very focused on daily cycling, multi-use cases, short and long cycles every day, with an idea that the main use of the battery is a bulk shifting of energy every day. And that way you get the most value out of that asset, and we can drive the life cycle cost of that down very low to be very competitive with lithium ion or any other storage technology in that longer duration. And when I say long duration, I'm typically talking 8, 10, 12 hours, where you spend most of the day either charging or discharging. We're headquartered just outside of Portland in Wilsonville, Oregon. We've got a big facility here, 250,000 square foot manufacturing plant. Over the course of the last year and a half or 2 years, we've been putting a lot of automation in for the battery module production and taking a lot of labor cost out, getting the cost down on the core components of this technology. Our plan by the end of 2025 will be to have an annual production capacity of about 2 gigawatt hours. But that's really just the start, because we're talking to people about specific projects that are that big. 8 hours adding up to 2 gigawatt hours in a single project. So in the course of 26 through 30, we fully expect to grow the capacity dramatically, both here in Oregon and with partners in Europe and Australia. We're already starting to do a fair amount of work in Australia. We're about 270 employees today, most of which are in Oregon. We do have some field service people in Australia, some people over in Europe, but the bulk of the employees are here in the US. We're strictly focused on the iron saltwater chemistry, and I'll touch on that. And we're a battery supplier. We're not a developer. We're not a integrator with PV or wind. We're trying to stay very laser focused on developing the ideal long duration storage battery that typically can be coupled with renewables. And we did go public a couple years ago on the New York Stock Exchange. So just a little background. When we talk about long duration, again, I'm talking about 8 to 12 hours daily cycling type stuff. There's longer duration stuff, pumped hydro in some cases. There's an iron air 100-hour battery you guys probably have heard of. And then there's certainly the lithium ion, which is typically inherently a 2 to 4 hour type duration at rated power. And so we're kind of in between those. And as I mentioned, we're really focused on applications where you can do more than one thing every day. And I'll touch on why, but it's in a nutshell, it's because we don't degrade with cycles, and therefore we encourage it being used. But amongst the long duration storage technologies, we're in electrochemical. There's other types of flow batteries. There's the iron air that I mentioned. And then there's thermal, where you're basically heating up some type of media and then drawing that heat off when you want to, and maybe driving a turbine, or depending on what level of heat you're turning that into electricity. There's mechanical, which obviously pumped hydro has been around for ages. That's a typical mechanical one. There's also lifting blocks and dropping blocks, and you've probably seen some of those. And then there's chemical type batteries also, which the hydrogen certainly plays a role in. So to talk about what we're doing here, starting with the chemistry of iron salt water. So we're dissolving iron into a saltwater solution. And one of the unique things of this is all batteries, as you know, have positive and negative electrolyte that are usually separated. And you take advantage of that separation to be able to generate power. In our case, the electrolyte is exactly the same on both the positive and negative sides. So when we are fully discharged, all the iron is back in the electrolyte. We have the same chemistry on both sides. So that offers an opportunity that should the pH balance get out of whack between positive and negative sides, we can just mix the tanks and get back to where we started. So I'm going to touch on a few ways that we get to the no degradation over time. And that's one of them, where with any flow battery, you have the opportunity to do some type of maintenance on the electrolyte and keep it fresh. Obviously, with a lithium ion or any cell type battery, you just have to treat it well and hope that it doesn't degrade faster than you expected it to, because you can't do any maintenance inside the battery. In this, in the implementation that we have, what we're doing is on the negative side of each cell, we're electroplating iron onto the negative electrode when we're charging the battery. And then when we discharge, we very carefully dissolve that iron back into the electrolyte. So very repetitive. It's not rocket science in terms of the electroplating or the deplating. It's not necessarily rocket science, but the intellectual property that enables us to have a unique position here is there's always side reactions with every charge and discharge cycle. And being an aqueous chemistry, hydrogen evolution is one of the main side reactions that happens when we're charging and discharging, but primarily on the charging side. And where our intellectual property is we have a electrolyte health management system that basically rebalances by putting that hydrogen immediately back into the electrolyte. So if you imagine hydrogen evolving out of the battery module that's blown up there, it's a closed loop system. It goes right back into what we call a rebalancer, which is over on the left-hand side of that container. And that essentially moves the hydrogen back into the liquid electrolyte. It's simple but elegant kind of solution to a closed loop system to enable us not to lose power or capacity cycle to cycle or over time. So those are kind of the two main things that are going on. We've got the rebalancing automatically happening as we're cycling. And then if we do need to get the pH between the negative and positive side back in balance, we can actually take an individual unit and do a mixing of the two sides of the electrolyte. Any questions on the core technology? I guess the other thing, a couple of things I'll mention here. We operate fairly warm. The ideal efficiency is in that 55 to 60 C range for the electrolyte going through the battery modules. And we're exothermic, so if we're cycling every day, we're generating our own heat. We don't have to turn any heaters on to keep it going. If you're not using it every day and it's down for a few days, we do have tank heaters that can come on and keep it at a minimum of 40 C. And that's where we can get back into a cycle. And actually one full charge discharge cycle from 40 C can get it back up into the 55 C range. Because we're a fairly benign chemistry, we don't have any exotic materials in here. Most everything is plastic or plastic coated. And we use PVC plumbing. We use commercial off-the-shelf water pumps to push the electrolyte through the stacks. The stacks themselves have polypropylene plates. There's some membrane and bipolar carbon plates in there, but truthfully, it's not very exotic materials.
Bill,
I'll pause there. Go ahead.
yeah, there's a question. Paul has his hand up.
Go ahead, Paul.
Yeah. Hey, Bill. I was looking through the specs on it and I couldn't really find anything. What is the overall efficiency of the battery?
So I
Round
will
trip.
say with flow battery and with any flow battery, and especially with ours, it depends on how you're using it. If you're doing a full charge and then a full discharge cycle, and then you put it into long-term standby so you're not just sitting there running the pumps and not doing anything, it's about a 60% round trip efficiency.
Okay. That's I mean, most of my experiences with either vanadium or bromide.
Yep.
It's around 70 and below. Yeah, that's what I expected. Thanks.
Yep. And obviously, if you're doing other use cases like you're standing by to do a frequency reg fast response, you've got the pumps running. We got about 5% aux load, so that doesn't help your round trip efficiency if you're doing that. But you only do that if you're going to make a ton of money when that frequency event comes along. Okay, any other questions on technology? I'll kind of move on here. So what we're focused on with our products are 8 to 10 hours today. Mentioned the no degradation over time. The ideal target is to get the lowest LCOS over a 25-year period. These are designed for 25-year life. So the more you use it, the better you're going to look on an LCOS basis, levelized cost of storage. There's no need for augmentation. It's a closed loop electrolyte system. We don't lose any electrolyte. There might be a point in time where we have to inject some hydrogen if in the course of things, hydrogen finds its way out of the plumbing, which hydrogen is known to do. While we're primarily focused on bulk charge and discharge, we can respond and go to full power in less than a second with the pumps running and just in a run-ready mode. So that's where some of these other use cases can come into bear. Like if you're doing a bulk shifting of solar during the day and there's a need for a frequency response activity, you could easily jump to that within a second and then go back to your bulk shifting. So that's the flexibility for multiple revenue streams. Because we're at 60 degrees C optimally in the operating temperature internally, we go into warm environments, we don't need any air conditioning. It's just forced air ventilation going through the containers. That container I showed you as our first product, which is basically a turnkey 75 kW, 500 kWh, which is UL listed, and we've probably deployed about 80 or 90 of those to date. And then at the bottom line, from a sustainability standpoint, the manufacturing of these is very sustainable. We don't have clean rooms. We don't have hazardous chemicals to put these things together. The electrolyte itself is very sustainable and recyclable. It's basically food-grade iron that we use in there. So the product we're coming out with right now, that earlier product I mentioned was 75 kW, 500 kWh, so like 6 hours of duration. And it was really a compromise because we had to dedicate part of the container to the tank and part of it to power and the balance of system. Here, we're going to a true 8-hour system, 2 40-foot shipping containers, the lower one obviously having all the electrolyte, the positive and negative tanks, and the water pumps. The upper container, all these are the same components as in the other system that we have, but that has the power modules, the electrolyte health management system, all the DC-DC electronics, and the BMS. So these are individual building blocks at this level. And we built the first one in January. It's in testing at our facility. We're building the second one right now. In about September, October, we're going to hand that over to Portland General Electric, and they'll run it for 2 years on the distribution grid, doing various use cases. So this will be the first systems we put out there that are inherently 8-hour duration. And then we'll be in full production later this year. And we've already got a couple of utility projects in the 1 to 3 megawatt range that these systems will go into. This is an example layout, if you will, using that 2-stack container configuration. We call it the Energy Center. Each of those stacks can be about 3 or 4 feet apart. Really, the separation is only for ventilation. There's no chance of thermal runaway with the iron flow battery being an aqueous electrolyte. So there's really no fire risk that you have to have any separation on, which I think many of you are familiar with the setback requirements and separation on lithium ion. The other element of this is all the service is done from one side of these stacks. So there is a 16-foot service aisle to be able to get in and do any replacement of the stack if you have to, or get access to the containers. So you can see density-wise, it's 5 megawatts AC. We would put in about 5.8 megawatts DC, given the losses going through the inverters transformer out to the point of interconnect. And that takes up about 2/3 of an acre. So we're roughly, with this design, we're roughly 7 megawatts per acre with 8 hours of duration. So 56 megawatt hours of duration per acre would be the density. That's less than lithium ion, even with the fire separation, but no augmentation required. So when you start to think about augmenting lithium ion every 10 years or so, you're going to need more space, or you're going to spend a lot of money pulling systems and putting new ones in. Some of the applications that we are going into today, it's a pretty broad variety of things. Starting on the left side, this is actually in Australia. And this is a coal plant that's going to be shut down in the next 5 or 6 years. They're putting in a lot of renewables regionally in terms of wind, locally in terms of solar. And they feel they need an element of long duration storage there. What they're looking for is 10 hours of storage to try to get all the renewables plus the storage to kind of act as baseload power that they're giving up with the coal plants. This is a 1 megawatt demonstration project over there in Queensland. On the airside operations, this is actually at Schiphol Airport in Amsterdam. This is kind of a distribution grid capital deferral, if you will. They move from regular generation, fossil fuel powered APUs, which were providing electricity to the regional jets when they're on the tarmac, to lithium ion based battery APUs. But they got to bring them back and get them charged for the next round of regional jets that come in. And they had a limitation on the amount of power they could get out to the tarmac without a big upgrade to the airport facility. So what we're basically doing is trickle charging off of the distribution network. And then when they have rush hour, so to speak, the APUs are coming back to be recharged. We help recharge those. The utility scale DER, this is actually with Sacramento Municipal Utility District. They've got a 1 megawatt setup that we deployed about 6 months ago. We're actually going to build another project with them using that energy center that I showed you. And then over on the right side, that's behind the meter, a commercial business. It's actually a computer recycling facility where they're swiping old computers and reloading software and then reselling the computers internationally. It turns out that they bought it to kind of move the solar to the evening and reduce the use of the grid electricity. But what they found the most payback on is they had multiple outages from storms. And when they have all those computers being reloaded, if they have a blip, they have to restart. And so there's significant value in not suffering a grid outage inside the operation. So that particular one, they value the resiliency of it. And then I'll give you a little teaser. I've talked about the first two products. What we're working on right now on the right side is for very large utility scale. We have a contract with LEAG in Germany. They're a big coal-fired generation company who is getting out of the coal business. And they want a combination of lithium ion and long duration batteries to move, very much like the Australia utility I mentioned, move to renewables on a baseload power type scenario. Here we're taking the same components, we're getting rid of the containers because we're now talking about 50 to 150 megawatt facilities. And you really don't want to be shipping thousands and thousands of containers and let that steel just sit there at the site. So this will be built into an enclosure, and it actually increases the density, the energy density, quite a bit. We're probably twice the power density and 3 times the energy density. So we would be roughly about 15 megawatts per acre, and we could do 10 hours of duration, which would be 150 megawatt hours per acre. And that, as far as I'm aware of, is very competitive with lithium ion on an energy density standpoint. So that's where we're headed. We're working the initial design right now. We'll probably have prototypes of that in mid-25. And then LEAG is actually going to have us build a 50 megawatt plant. It's basically a purpose-built processing plant that's an iron flow battery in the 27 timeframe. So I think, yeah, the last one was just the specs on the two products that we're shipping today. And I can forward this, Noel, and get it. You can distribute it if you'd like. I think that was, yeah, basically what I had. So I'll let you leave it to questions you might have that I might not have touched on.
Serene, you posted a question in the chat earlier.
Yeah, I can read it off if you can hear me. So I have two questions, and one is more important than the other. But the first one is, might Hawaii be especially suited for iron batteries in any appreciable way? Because we have an equable climate and also have warmth.
Right, right. I heard the warm part. What was the first part?
Equitable. I think I might be saying it wrong, but yeah, it's like very, temperature modulated.
Yes, right. Yeah, yeah, the southern part of the U.S., Australia, the islands, you don't have to worry about air conditioning these units. Now, when we start to talk about going to the northern tier, if you're not cycling every day, we have to turn on the heater. We may, and that's where this battery in a building concept over on the right-hand side might make a lot of sense, because you can control the ambient around those units to, say 40 Fahrenheit or something like that. And you'd never have to worry about turning on heaters in the tanks.
Okay, and my second question is about how small do your systems go to? Because right now USDA REAP gives matching grants to $1 million for small business to, get battery storage. So I'm wondering if you guys are going to unscale.
We've looked at it. I would say it's very unpractical to scale down a flow battery to a residential scale, say a 5 kilowatt or something like that. So the smallest one we have is a turnkey container, the Energy Warehouse, which is at 75 kilowatts. And so our focus really is on scaling up. I would project that 5 years from now, we would be very focused on doing 100 megawatt and up size plants with this technology. The efficiency of that and the cost effectiveness of that kind of drives you in that direction.
Understood.
As much as I'd like to have one at my house, but I need a footprint of a 40-foot container.
So I was wondering about, since they are in containers, how they deal with the salt fog and rust issues of the container itself, and
Absolutely.
the racking and the components.
Yeah. So one of the real advantages of the core part of the battery is it's mainly plastics. We really don't have metals that are in there. Obviously, a container there's plenty of examples around the islands of containers that rust after a year or two. So from a container standpoint, putting special paint on initially, and then doing annual maintenance of attacking any rust that shows and repainting, I think from a cosmetic and a structural standpoint, will be the strategy for 25-year type lifetime. Internally, we are looking at some projects on islands, and I think we have to prove to ourselves by doing that we don't have any issues with like DC-DC converters and PCB boards and things like that are embedded inside the container. I know inverters learned an awful lot in the early days of solar about what that environment is like.
Do the containers come with a salt resistant coating, or is that an adder? Or
it would be a special paint. Yeah.
So
we
that could
typically
be ordered.
we've done stuff in California, but I don't think anything is even as close as 10 miles to the ocean right now.
Yeah, it would be destroyed in Hawaii and American Samoa, Saipan, Guam.
I spent a little time over in American Samoa, so I know what you're talking about.
American Samoa is the most harsh salt fog there is, as far as I know, because of the temperature inversions there.
Yeah. So yes, that is something that we've had discussions about. We need to throw the unit into that environment and start to learn from it.
I got a site.
And as you probably know, Vicki, I'm talking to the Idaho National Lab folks.
Did that ESTC project go anywhere? I haven't heard back.
It's still in process.
Okay.
Yeah, they got a thumbs up to deliver a proposal.
They asked for a proposal? Excellent. So that's the next step. Great.
Yeah.
Thank you.
Yeah, so that would be an ideal candidate to get a couple of these systems out there and run it through the environmental basis.
All right, reach out to me next week and we can talk a little bit.
I will. I actually have a call, I think Tuesday, with
Justin?
Jeremiah.
Hey, Bill.
Yes.
Question about clearly there's quite a bit of an advantage that this technology would have with regards to demand for resources, right? If you compare it with the traditional lithium ion solutions and the other solutions that are out there. Yeah.
Scarce resources,
So
yeah.
I'm just wondering, as you're going forward with socializing this with potential customers, do you have material that can quantify? I know you can speak to the differences in the components that are being utilized and the electrolytes that are being utilized, but is there something that quantifies the actual impact, like environmental impact? If you go down this route, you've got less of an impact from a carbon perspective, from a natural resource dependency standpoint, that sort of thing. Is that quantified?
I haven't seen it when you go back to the mine. You start there. University of California, Irvine did a study of flow batteries and lithium ion from a manufacturing standpoint. So assuming you have all the materials and you're going to build a battery, what is the sustainability of that? And then they looked at it through the life of the battery. Obviously, we came out very well in that. There's no clean rooms involved in assembling these things. It's kind of like if you think back to what the old car factories looked like, where you're just bringing components together in a, not necessarily a dirty warehouse, but a non-clean room area. So it's came through very sustainable from that standpoint. I would tend to think that it would look pretty favorable. Mining lithium is not that great. Vanadium is really a byproduct of some of the mining or steel production, but it's expensive.
Yeah,
and
I was going to just kind of tag on to what Noel was saying, which is that one of the issues surrounding the CRT, resources that go into the alternatives that don't use iron, is the geopolitical issue.
Absolutely.
Because it's very concentrated, and I don't think there's another metal that's as ubiquitous around the world than iron. So you're in a very good position in that standpoint.
That's the most prevalent iron or metal around the world.
Yeah.
And on the other end, like you talked about, cobalt, for example, there's very few places that really have much of that, and they aren't very attractive places.
And they've been bought up by the Chinese.
Right. As have any rare earth type materials, which we definitely wouldn't use. So Gary, you got a hand up.
Bill, thank you so much for your presentation. We talk a lot about hydrogen, and there are a lot of people on this call who are very sold on hydrogen, and I've been researching it, trying to catch up. And one of the things which comes up again and again in my research, and again, I'm an amateur, is the hydrogen leaking out of the system and it being very, very difficult to contain and work with. You mentioned it as something briefly in your presentation. Can you speak from a practical standpoint as how concerned are you about that? And from an installation standpoint, how much has that been an issue?
Yeah, so there's really two concerns. One is economic. If you have to go and put more hydrogen in, it costs you something to do that. The other is safety. And, we spend a lot of time worrying about the safety aspects of this. Being a closed loop system and very low pressure, we're operating at maybe 5 PSI at the most in there. I think it's typically in the 2 or 3 PSI range. There isn't a lot of hydrogen that can evolve out of the closed loop plumbing, but ultimately there is some, and that's where we will have to come in and augment a little bit with juice it, the electrolyte a little bit with hydrogen. There's been lots of design work and studies and UL review of the ventilation that we have going through these spaces to make sure that there's no buildup of any hydrogen, even if we had a catastrophic leak. There is a vent on the outside of the container that if it overpressures, there's a burst disk and it can vent. So we actually meet the UL requirements, and we're even more stringent requirements over in Australia. AS3000 we've designed to, from a safety standpoint.
I think Stan's got his hand up, and Vicky too.
I'd like to add my compliments on your presentation, Bill. What is the pH of the electrolyte, and is it something that we would worry about if we had a spill, or we had something we had to use an environmental, response team or something like that? And we found in terms of actually, we're surrounded by 2,500 miles of salt water. So it's like, is that something we could take advantage of because of our location?
Well, we have a recipe that we put salts in there with a certain level. We aren't just throwing salt water in, we're creating the salt water. The pH will vary with the state of charge. And so typically between 2 and 4. So at 2, what is that, stomach acid level? It's not going to be hazardous to people, but you're not going to want to leave it on the ground. You're going to want to put some lime on it or something like that to neutralize it. What we found in most jurisdictions is there is a requirement for secondary containment, which isn't a surprise. Vanadium has that and the bromine ones. In that energy center design, we actually built secondary containment into the lower container. So whereas the energy warehouse, you'd have to put some kind of curb that would be a part of the foundation to act as secondary containment. In the energy center, you don't, because we have that secondary containment integral to the lower container. I've seen videos of putting the electrolyte into vanadium batteries, and they're hazmat suits. Our guys don't wear hazmat suits when we put it's basically ferrous chloride, which is used in wastewater treatment, and only we make sure that the iron is very pure. It's electrolytic grade iron, and salts, and then we add DI water. So it's a relatively benign, but it's not neutral.
Thanks, I appreciate it.
Mm-hmm.
Hey, Vicky, yeah, sorry, your hand was in the bright part of your curtains behind, so it's hard to see it.
It's okay. Bill, this is a naive question, but I'm hoping that you can ship the unit without the fluid in it, and you can create the electrolyte on site with DI water. Is that possible? Or
absolutely, that's a great question. We definitely do not ship it with electrolyte in it. When we're doing the end-of-line testing at the factory, we'll fill it up with electrolyte and run it through its final acceptance test. But we take all the electrolyte out. We may or may not put dry salts in the tank for shipment. We've done it both ways, but there's no fluid. And then we bring concentrated ferrous chloride to the site and then add that to the tank and then add DI water to the tank. So it's really mixed at the site. And it would be very heavy shipping.
Yeah, it would be very heavy and hazard just because it would slosh on the ship because it's got to go by ship. So
exactly.
It should lower the shipping costs. Although is ferrous chloride considered a hazmat when you're shipping it? Is that
it is? But ferrous chloride you can get just about anywhere. Not, I would back off and say not every island's going to have it, but we have a source now that's qualified in Queensland, Australia. We have a couple sources here. We actually make it. We have, Portland's known for microbrews. We have a homebrew facility here that we make it on site. And so, yeah, I will have the same capability in Europe, and the major regional areas will have local. So we don't have to ship it via ocean. But for Hawaii, Pacific Islands, we would have to ship the concentrate.
Hal's got a question now.
Yeah, Hal.
You're muted.
There you go.
I have two questions. One, the first is you mentioned that you weren't successful so far at scaling it down to a residential use. But I'm curious, could it be scaled to such a point that it could be shared amongst, say, 5 or 6 or 7, however many residences would fit with the output of the unit?
Yeah, basically you're starting to talk about a microgrid where several different metered facilities or homes or whatever are behind a single point of interconnect to the grid. And it's an ideal situation to sit behind that point of interconnect and be an asset that could be used by each of those separate meters, separate facilities. You just have to size to the loads and the load profiles that you expect at each one.
And my second question is, what's the potential for recycling at end of life?
It's very good because the electrolyte doesn't degrade. We could go use the electrolyte in another iron flow battery. If you wanted to recycle the electrolyte, you just precipitate the iron out of it, and you've got food grade iron, which can go into Kellogg's Wheaties or whoever it is that makes Wheaties. Like I said, most of the internals of the battery itself are polypropylene plastics, so those can be recycled.
Okay, thank you very much.
And PVC plumbing, that's obviously something that can be recycled.
Thank you.
Mm-hmm.
Ron Riley, you posted a question as well.
Yeah, let me ask, this may be a real naive question, but with Oahu and the other islands going more and more to wind and solar, there's been an objection or a concern, I should say, that we can have a long series of windless, cloudy days. Somebody knowledgeable said just the other day on a webinar that could be up to as many as 45 days. And if you cut the wind and solar generation out for Honolulu for 45 days, how much battery are you going to need to keep all the lights on? Is this within the realm of feasibility or not? I just have no idea.
You may want to keep that power plant over in outside of Honolulu on reserve for something like that. Because the affordability of trying to have a week or 2 weeks of energy storage is quite expensive. I mentioned we're really focused on the daily cycling, so we're, in that energy center, we've got 1.2 megawatt hours of energy. So if you were in a situation like that and you just trickle discharge out at maybe you got a 30 kW load, you could go a long time, but you can't go weeks with this technology. And even if you went down to discharging at only a couple of kilowatts, your aux load is going to be bigger than your load. The aux load for running the pumps. So there's a point where you just can't go any longer.
Okay.
And
great.
I would
Thank
say
you.
it's probably in the 3 or 4 day range with the 8-hour system. But I would really question 40 days in Hawaii without sunshine. Maybe if you're under the black cloud over in Kona or something like that. But
that kind of thing is I mean, for here in Honolulu, that's kind of a stretch. I mean, it would be once in 500 years, but it's not an uncommon situation in northern latitudes in Europe and say Canada and Germany and Finland and areas like that, where that is a very real issue, where where the issue of 4-hour storage or 8-hour or even 12-hour storage is really conservative on a regular basis. Is there, where, I know that there's that really long duration storage is an issue that really has not found an equitable solution. Is this would this be more suited to that than some of the other chemistries that are more prevalent these days?
Well, so if you think about what we're doing when we're charging and discharging, we're a little different than other flow batteries in that there's 2 things that limit our duration. One is the amount of electrolyte you co-locate with the batteries, how big the tank is. And the other is the spacing that you have between each cell, because we're building up a thin film of iron when we're charging it. And there's a limit to how thick we can make that unless we redesign the battery to have much wider spaces. But then you're getting into all kinds of trade-offs. We've found that the sweet spot is that 8 or 10, 12-hour range in terms of the thickness of the electroplating and the amount of electrolyte that we have to co-locate in a tank. I mentioned earlier, I'm not in the business of touting other technologies, but there is the iron air technology out of Forum Energy that is really geared toward 100-hour discharge. Now you have to recharge in about 200 hours, but that is a technology that's really oriented toward longer outages of renewables. And it's just now being tested by a few utilities in the States, I know.
Yeah, I mean, as you mentioned earlier, hydrogen is really, is a prime long duration storage medium. So there are alternatives.
Exactly.
It's a matter of dollars.
And even when it's cloudy, the PV systems do charge a little, so you'll be trickle charging the battery. It's not going to be null. There will be some charge.
Yep. No, you're exactly right.
So I think 45 days of absolutely no charge from a PV system it has to be damaged. You'll get some charge, which will help your pump running.
And some of the things we're working on for the next generation, well, one of the key things that relates to what we're talking about is the ability to fast charge the battery. So if you've got an 8-hour discharge today, it takes us about 10 hours to recharge it, given the round trip efficiency. With a fast charge, we charge at a much higher power level. We can charge that 8 hours in about 6 hours. So now you're starting to grab the peak of the solar day. And if you have clouds coming and going, you can get more energy out of those sunny hours into that battery. So I think that will help in those situations. Also, just for market arbitrage, when there's negative pricing, you get out there and you grab as much energy as you can in that period where there's either very low or negative pricing, which I don't think you see in Hawaii. Maybe you do at this point, but certainly you do in California and in the Southwest with wind. There's a lot of periods when there's negative pricing on the market.
So Stan, and then Kyle, because I know Stan, you've had your hand up for a bit.
Yeah, two quick questions, and one may not be applicable. I was told when we first started looking at flow batteries a decade or so ago, that one of the advantages of them is you can charge and discharge at the same time. Is that applicable to your system? Or is it even valid? And number two,
it's funny because you're definitely not the first one that has asked me about that, and you cannot. We're just looking for a change in polarity to the battery. So you're either drawing current or you're pushing current into the battery. As I mentioned, we can actually at the battery level, it's 6 or 8 milliseconds switch time. The thing that makes the spec be less than a second is all the communication that goes on between the BMS and the inverters and all that. So it can switch very fast. But I'm having a hard time understanding the use case where you would want to do that. That's what keeps coming to mind whenever somebody asks me that is, why would you, under what circumstance would you want to be charging and discharging a single battery at the same time?
Yeah, we were actually looking at possibility of having a segregated microgrid where part of it was using the battery and we still wanted to capture solar and do it. So it was just a discussion item 10 or 12 years ago.
Well, the way we would do it is two systems.
Yeah.
One could be charging when the other one's discharging.
And my second question, which is also probably obnoxious and nonsensical, is regular batteries discharge when they just sit there, but yours, unless you charge it up, does it discharge without a load?
If the pumps are running, it has about a 5% internal auxiliary load, parasitics.
A parasitic load. Okay.
Yeah. So the strategy that our customers use is you run the pumps when you know you're going to be charging and discharging. when you know you're going to have it turned off for 1 to whatever number of hours, you go into long-term standby. And it's just a simple command to the BMS, and it gracefully shuts down the battery, drains all the electrolyte back into the tank, and basically puts it to sleep like your DVR. And then you've got maybe 100 watts of load, or, it's very low. So it would not degrade, or the capacity wouldn't go down much in that mode at all.
All right. Thanks very much, Phil.
Yeah.
Kyle?
Thanks. Hey, Bill, 2 questions for you. One, tagging on to the last one, do you think, is it possible to reduce that parasitic load with scale? That is the proportion of the load from these pumps compared to the capacity of the batteries. And then 2, do you foresee some improvements, incremental or otherwise, to round trip efficiency in the near future? I'm sure it's something you're working on.
That's great. Yes, when we start to look at this battery in a building, or the concept I talked about that we're working on, there are efficiencies gained by having larger pumps with much larger electrolyte tanks feeding more battery modules. So there are efficiencies that we would expect in that sense. There's also some things that we're looking at managing the hydrogen in a different way, not at the individual building block level, but more at a facility level, which could also improve not only the efficiency, not only the aux load, but also the efficiency of the system. Your second question, yes, 60% round trip efficiency is not acceptable in the long run. And we do have a whole bunch of development projects going on toward improving that. I would say in the next 3 to 5 years, you could see that go up easily 5 points, maybe more, just with technology improvements and material improvements and things like that. The other thing I didn't mention, and this kind of made me think of it, is back in September of last year, we entered into a partnership with Honeywell, a small Fortune 100 company. And they were actually working on an iron flow battery themselves for a number of years, and finally decided that they might be better off if they joined company with us. And so they made an investment in us. We're collaborating on not only taking product to the market, to their customers and their controls expertise, but collaborating on the materials and some of the core technology elements that they have an army of scientists where we just have a handful. So that's encouraging us on, we're going to find ways to really improve this thing over the next couple of years.
Love it. Thank you.
Carolyn?
Any idea of the earthquake rating of the stacked containers?
That's great. So we designed it for the primary customer we had in mind when we were designing it was SMUD, the Sacramento Municipal Utility District. So we have designed it, and we've actually gotten certified to, was it level D? I'm forgetting the right designation, but it can withstand earthquakes and still be operational in the Sacramento area, which I think is Class D, if I remember right. So we could probably be over on the Big Island, relatively close to the volcano, and survive, as long as the lava doesn't cover us. I remember watching the lava come toward that geothermal plant south of Hilo. Near where you are in Volcano, I think, Ron.
Yeah, that's right.
Yeah.
What about typhoons, wind load?
Wind load, it's designed, so part of the strategy for both seismic and wind loading on the double stack container is we put tie bars on the ends that tie it cross-sectionally to the foundation. And with that, we're rated 150 mile per hour wind and then the seismic D. We don't put the tie bars on every location. Obviously, if you're not worried about those kind of winds or earthquakes. In that stack, it's about 200,000 pounds total weight when the electrolyte's in there. And I would bet that 70% of that weight is in the lower container. So it serves as a good anchor for the top container.
Well, thank you so much for taking time to share this technology with us.
I appreciate the opportunity. Thank you, Noel.
Yeah, the many different advantages that you've socialized here, right? In terms of the cost effectiveness, the lifespan, scalability. When we talk about enabling affordable energy for our communities, the cost of the solutions certainly play a big part in that. So if we have the opportunity to have long duration storage augment, our intermittent renewables that we currently have, that's going to play a potentially a big role in decreasing costs. So really appreciate that. And clearly, based on what you shared, there are certain applications where this would be very advantageous, and others where it wouldn't be. So it's one of those things where looking for the right application and then proposing a solution would be a very, very important exercise. So really appreciate this.
Yeah, no, my pleasure. And if anyone has further questions, I think in the meeting, attendees list for the meeting, you've got my email. And I'll forward this presentation to you, Noel, and you can distribute it.
Will do.
Yeah, I think you're right. There's all kinds of different energy storage solutions, just like there's all kinds of different generation solutions, and coupling that up with the right application is key. We're not the holy grail for everything, and amazingly, lithium ion isn't the answer for everything also.
Agreed. Thank you.
All right. Well, thank you very much.
Well, team, thanks very much for joining. And Bill, I know it's really late out there. Or you're on the you're in California, right?
In Oregon.
Oregon, yeah, that's right.
Yep.
So have a great evening. I really appreciate you taking time out later in the day to enlighten us here. Thanks very much. And everyone, this is going to be published on our website, and we'll also send out the the link to the attendees. Thanks very much.
Thank you all.
Thank you.
Have a good weekend.